Hello my friends, and welcome back to the Today Machine channel.
Nucor Corporation revolutionized steelmaking in 1969 by introducing the mini mill, which uses electric arc furnaces, EAF, to recycle scrap steel into new products. This method marked a departure from traditional blast furnaces, which rely on iron ore as the primary raw material. The process begins in the scrapyard, where different types of scrap are sorted and combined to meet specific customer requirements. For advanced products, scrap is mixed with direct reduced iron, dry, which Nucor produces using natural gas. This not only enhances steel quality but also ensures environmental sustainability, making Nucor's steel among the most eco-friendly on the market. The sorted scrap is melted in EAFs at temperatures of 3000 degrees Fahrenheit, a more energy-efficient process than traditional methods. The molten steel undergoes chemical refinement before being cast into billets, slabs, or blooms. These initial forms are then processed in rolling mills, where slabs are heated to 2200 degrees Fahrenheit and reduced under immense pressure to create products like steel sheets. For example, a 3.5-inch thick slab can be transformed into a quarter-inch thick, 1,300-foot long coiled sheet in minutes. Entry section. The entry section of the mill plays a crucial role in preparing the steel coil for the production process. It begins with the coil car, which transports the steel coils to the uncoiler. The uncoiler unwinds the coils and prepares them for further processing. The next step involves the hold-down roll, which ensures that the steel coil remains stable and controlled as it uncoils. After uncoiling, the coil peeler removes the edges of the coil to ensure clean, smooth material enters the forming section. The pinch leveler straightens the coil to remove any curl or twist, ensuring uniformity. The crop shear is used to cut the steel coil into manageable lengths, while the skewed conveyor transports the prepared coils to the next stage. Finally, the edge miller trims the edges of the steel to remove any irregularities, preparing the coil for the forming section. Forming section. The first stage is the transition and breakdown stands, which begin to form the coil into a more consistent shape. The transition stand helps guide the material from a flat state into a cylindrical shape, while the breakdown stand performs the initial roll forming to reduce the thickness of the steel. The edge bending stand further refines the edges, ensuring they align correctly for welding. The cage roll stand is used to stabilize the tube as it progresses through the mill, while the computerized roll positioning system, CRP, automates the precise alignment of the rolls. The fin pass stand completes the final shaping of the steel before it enters the welding section. Welding section. The The process is supported by the squeeze roll stand, which applies pressure to ensure the weld is strong and uniform. After welding, the inside bead cutter removes any excess material from the inside of the tube, while the outside bead cutter removes any material from the outside. The scrap winder collects the discarded material for recycling. To further ensure the quality of the weld, the tube passes through an inline ultrasonic test (UST) to detect any internal defects. The seam annealer heats the welded seam to relieve stresses and improve material properties. A pull-out stand then helps pull the tube through the cooling and sizing sections. Cooling section. The air cooling stand initially cools the tube using ambient air, while the water cooling stand further reduces the temperature by applying water. This controlled cooling process helps prevent warping and ensures the tube retains its shape as it moves into the sizing section. Sizing section. The sizing stand ensures that the welded tube reaches the exact dimensions specified. The Turk's head stand further refines the tube's shape, ensuring that it meets the required specifications for both size and roundness. Following sizing, the tube passes through an inline marking machine, which prints the necessary identification and quality control marks on the tube. The flying cutoff machine then cuts the tube to the required length, while the pull-out roll stand ensures it moves smoothly through the cutting process. Finishing section. The finishing section is where the final touches are applied to the tube. The flushing unit cleans the inside of the tube, removing any debris or contaminants. The tube then undergoes end facing and chamfering, where the ends are prepared for threading or other finishing processes. The kick-in and receiver system ensures the tube is securely held as it moves through the process, while the kick-out and roller conveyor assist in handling the finished product. The tube undergoes a hydrostatic test to check for leaks and ensure structural integrity. For additional quality assurance, an offline ultrasonic tester is used to perform a more detailed examination of the welds and material quality. Additional processes. Once the pipe has passed all the tests, it may undergo further finishing processes. The varnish coating machine applies a protective coating to prevent corrosion. The end cropping machine trims any excess material from the ends of the pipe, while the threading machine may be used to prepare the pipe ends for connection. The power tightening machine is used to ensure that connections are tight and secure. Bremen Machinery and Plotwalserige Pent introduced a new plate rolling machine into their operations. This state-of-the-art 3-roll plate bending machine boasts exceptional capacity and capabilities. Manufactured by Hausler in Switzerland, the construction of this impressive piece of equipment required a lead time of 18 months. Weighing in at 320 tons, the machine demanded a specially designed foundation to support its massive structure. This advanced rolling machine showcases numerous possibilities for handling metal plates. Before rolling, the flat plate features slight overlengths on both sides. This overlength is essential for creating precise edge contours, ensuring a perfectly round final result. These edge contours must be applied with meticulous accuracy. Once the edges are properly prepared, the plate undergoes careful marking for cutting. To ensure optimal cutting results, the plate is preheated. During the cutting process, the overlength is removed and welding edges are simultaneously formed. After trimming and shaping, the plate is ready for rolling. The rolled shell from this machine achieves an external diameter of 2076 millimeters. The welding of the seams is performed using a highly productive method that ensures rapid and efficient filling of the joints. In some cases, welding is done with two filler wires simultaneously, further accelerating the process. The welding wires are coated with a protective powder layer, and any excess powder is recycled for reuse. The bending press at Plotwal-sur-Rege Pent is among the heaviest in Europe, boasting a bending capacity of 3,000 tons over a length of 8,000 millimeters. With a bending force of 800 tons per meter, it can handle even the most challenging tasks. For example, it has successfully bent a stainless steel plate measuring 60 millimeters thick and 7.2 meters long into the required radius. As a testament to the machine's strength and versatility, it recently rolled a 43-ton steel plate with a thickness of 150 millimeters and a width of 2,230 millimeters into a diameter of 5,000 millimeters. This incredible feat highlights the expertise and capabilities of Bremen Machinery and Plotwal-sur-Rege Pent. The HDR3 roll plate bending machine is a versatile and robust solution designed for precision bending of metal plates. Its variable geometry and unique design provide unparalleled flexibility, allowing the bending of both very thick plates and small diameters with excellent quality. The HDR's most notable feature is its variable adjustment of rolls, a key to its superior performance. The two bottom rolls can move independently in a linear fashion, while the top roll adjusts vertically. This arrangement allows for a wide range of bending operations, including cone bending through inclined roll settings. The machine's flexibility extends to the adjustment of deformable wall thickness, which depends on the relative position of the bottom rolls. A symmetrical arrangement of the rolls maximizes deformable thickness, while slight asymmetry allows for handling longer flat ends efficiently. This adaptability reduces force requirements, enabling the bending of even the thickest plates economically. The HDR is engineered for durability and stability under heavy loads. Its compact, closed base frame ensures maximum rigidity against bending forces. The rollers, made from high-alloy, non-surface hardened steel, are exceptionally stable and crack-resistant. The rollers are driven by a high-quality 3-roller drive system, ensuring precise material handling and excellent traction. The automated forging line for train wheel production begins with the precise loading of the wheel blank. A manipulator ensures the blank is accurately positioned at the center of the press dies, preparing it for the forging process. With 9,000 tons of pressing force, the blank is shaped into a profile suitable for rolling, with the process guided by industrial robots that cool and lubricate the dies. The forging process uses state-of-the-art technology, where the wheel blank is rolled without a mandrel, guided only by web rolls, pressure rollers, and lateral rolls. This allows for a smooth material flow, and real-time corrections to tool settings can be made during the process. The rolling machine operates in a fully automated manner, optimizing the material flow and ensuring precise shaping. After forging, an innovative needle embossing tool marks the wheel with identification text. The wheel is then transferred to a measuring machine equipped with advanced 3D laser technology to ensure it meets strict dimensional standards. A continuous automation and tracking system monitors and documents the quality of the wheel, while specialized software adjusts the forming machines for optimal performance. This highly efficient automated system produces up to 280,000 high-quality railroad wheels annually, with diameters ranging from 700 to 1,350 millimeters. The result is a perfectly forged and tailored train wheel suited for its specific application, ensuring durability and performance on railways worldwide. The SMX series of hydraulic radial forging machines from SMS Mayer exemplify high-performance quality, precision, and flexibility. The SMX technology is trusted by leading companies such as Vitkovice Hammering in the Czech Republic, showcasing the impressive capabilities of the SMX 818 meganewtons model. With a maximum press force of 18 meganewtons, a tool opening of 800 millimeters, and an ingot capacity of up to 8 tons, the SMX 818 meganewtons is engineered for versatility and precision. It can forge products with diameters as small as 130 millimeters and lengths up to 18 meters. The entire process is automated, ensuring exceptional efficiency and consistency. After the ingot is removed from the furnace, it is positioned precisely by a manipulator to ensure accurate loading. The automated forging process, calculated using the ComForge software, begins. With a database containing flow curves for over 400 materials, the software optimizes the forging sequence to achieve a homogeneous microstructure across the entire radius of the material. Manipulators and carriages work in perfect synchronization, transferring the workpiece seamlessly and ensuring consistent forging results. The SMX is capable of forging round, square, and octagonal long products, as well as flat items with varying edge profiles. It can even forge seamless tubes with wall thicknesses under 30 mm and produce complex forms like step shafts and railway double axles, all in a single heat. The innovative press cylinders deliver up to 240 strokes per minute, depending on the machine size. This high-speed capability enhances productivity while maintaining excellent surface quality and precision. The near-net shape forging process minimizes machining requirements, saving both time and material. SMX machines are ideal for producing components like high-speed train axles, aerospace parts, offshore pipes, and energy plant components. They are energy efficient, environmentally friendly, and ensure high material yield. By achieving near-net shape production directly from the ingot, they reduce waste and maximize economic advantages. The GE Treveni 35 MW assembly reaction turbine is engineered for high performance in steam-driven power generation applications. Operating at a steam pressure of 24 kg per square centimeter, the turbine incorporates high-precision aerodynamic blade profiles, ensuring optimized efficiency and performance across various operating conditions. The turbine's design features a compact 20-stage configuration, combining advanced engineering techniques with robust performance standards. This includes high-pressure inner casing keys that enhance the structural integrity and overall performance of the turbine. Furthermore, the turbine employs a 7-stage high-pressure design, significantly improving steam efficiency. The advanced 3-stage labyrinth covers and improved labyrinth seals are crucial for minimizing steam leakage and enhancing the turbine's efficiency. Trigeny Turbines ensures the reliability of their turbines through rigorous testing procedures. High-speed rotor balancing and resonance testing are carried out to eliminate vibrations and ensure stable operation. These measures not only optimize operational efficiency but also extend the lifespan of the turbine by reducing mechanical stress. The combination of a high-pressure design, advanced sealing technologies, and extensive testing procedures results in a turbine that delivers high reliability, improved steam efficiency, and long-term operational performance. Initial preparation, store plates and numbering. The journey begins with the storage and preparation of steel plates. Each plate is carefully numbered to ensure traceability throughout the production process. Edge milling. To prepare the plates for forming, edge milling machines are employed to remove irregularities and ensure the edges are perfectly smooth. This step is crucial for achieving seamless welding later in the process. Plate forming, 3-roll machine and post bending. The plates are shaped into a cylindrical form using a 3-roll machine, followed by post bending to refine the curvature. This stage ensures that the steel plates attain the precise cylindrical geometry required for pipe manufacturing. Tack welding. Once the plates are formed into a pipe shape, they are temporarily joined using a tack welding machine. This preliminary welding holds the structure in place for further processing. Internal and external welding. The pipe undergoes comprehensive welding both internally and externally using advanced welding machines. Internal welding is performed first, followed by external welding, ensuring a robust and reliable joint. These processes guarantee the structural integrity of the pipes. Visual inspection and pre-washing. After welding, the pipes are visually inspected for any defects or inconsistencies. They are then pre-washed to remove impurities and prepare them for subsequent stages. Expander and post-washing. An expander machine is used to enhance the dimensional accuracy of the pipes and relieve internal stresses. Following this, the pipes are subjected to a post-washing stage to ensure they are free of contaminants. PE hydrotest machine ensures the pipes can withstand high internal pressures. Ultrasonic welding detection detects welding defects using ultrasonic technology. X-ray real-time machine provides detailed imaging to verify welding integrity. End finishing. Beveling and final inspection. The pipe ends are beveled using specialized machines to prepare them for joining operations. Finally, a thorough inspection is carried out to ensure the pipes meet all quality standards and client specifications. Sawing machine. The first step in the forging process is to cut brass billets into manageable lengths. This is accomplished using a sawing machine, which is designed for precise and efficient cutting. The sawing machine ensures that each billet is of the correct size for subsequent operations. It typically uses a high-speed saw blade to make clean cuts, minimizing material waste and ensuring uniformity in the billet dimensions. Graphitizing. After the billets are cut to size, they undergo a process known as graphitizing. This step involves coating the billets with graphite, which serves as a lubricant during the forging process. Graphite helps reduce friction between the billet and the die, which is crucial for producing smooth, high-quality forged components. The graphitizing process also improves the flowability of the brass, ensuring that the material can be shaped more easily when subjected to high pressure. Heating furnace. Once the billets are prepared, they are moved to the heating furnace, where they are brought to the appropriate temperature for forging. The furnace, often referred to as a billet heating furnace, uses controlled heat to raise the temperature of the brass to a point where it becomes malleable and suitable for forging. Proper heating is essential for achieving the desired material properties and ensuring that the brass flows evenly during the forging process. The temperature must be precisely controlled to avoid overheating, which could lead to defects in the final product. Forging press. The final step in the process is the forging itself, which is carried out using a forging press. In the case of brass, an eccentric press is commonly used. This machine applies immense pressure to the heated billet, forcing it into the shape of the die. Closed die forging, also known as impression die forging, is a highly advanced metalworking process where heated metal is placed between two or more custom-shaped dies. As the dies close under intense pressure, the metal fills the cavities of the dies, producing a component with intricate geometries, excellent mechanical properties, and minimal material waste. This technique is especially valued for creating high-strength, durable components for demanding applications like automotive, aerospace, and heavy machinery industries. Pioneered and perfected by Japanese craftsmanship, closed die forging has reached a level of technical sophistication that blends precision engineering with artistry. One of the most remarkable innovations in this field is the production of cracking connecting rods. Connecting rods, critical in transforming the explosive energy of an engine into rotational torque, traditionally consist of two separately manufactured components, rod and cap, later assembled. However, the unconventional approach of forging a single-piece connecting rod and then deliberately cracking it into two halves represents a groundbreaking achievement. The process begins with the forging of a single, robust connecting rod. Precision is paramount as the component must possess the perfect structural integrity and mechanical properties to withstand the engine's rigorous demands. The rod is then cracked along a carefully controlled fracture line, creating two perfectly matching halves. This technique ensures higher assembly precision and reduces weight compared to conventional methods. The resulting part not only exhibits exceptional strength but also optimizes performance in high-stress environments. This innovation reflects the ingenuity and mastery of Japanese forging craftsmen. For centuries, blacksmithing tradition has been driven by an unwavering spirit to push the boundaries of metalworking. This spirit manifests in every forged component, channeling unseen strength and durability into tangible creations. The extra heavy-duty plano-type lathe machine from Tirupati CNC is designed specifically for the precision turning of long shafts, making it ideal for industries such as shipbuilding, heavy machinery, and energy. The machine features a robust, rigid structure with a wide bed and a sturdy carriage to handle large workpieces. It utilizes a plano-type configuration, where the cutting tool moves along a fixed guideway while the workpiece is clamped and rotated on the spindle. Equipped with advanced CNC controls, the machine ensures high precision and consistency, It supports various operations, including facing, turning, and threading, with customizable speeds and feeds. Hydraulic or pneumatic tailstock enhances stability, and a coolant system optimizes tool life and surface finish, delivering efficient and accurate machining. The hot forging process involves shaping heated metal into desired forms using immense pressure. A 12,500-ton hot forging press line exemplifies cutting-edge technology in producing large and complex components with exceptional strength and precision. At Balzer's Forging, the 12,500-ton hot forging press line is tailored for the forging of front axles and other critical components from unmodulated steel. Once heated, the billets are fed into the forging press line through automated systems, ensuring consistent material handling and minimizing human intervention. The press exerts immense force, shaping the billet into the desired form through dies designed for precision and durability. Key features of the forging line. Automation. The line integrates automated unloading systems for front axles, reducing cycle times and enhancing efficiency. High force capacity. With a press force of 12,500 tons, the system can handle large-scale and complex forging tasks, ensuring uniform deformation and superior mechanical properties. Material optimization. By using unmodulated steel, the process optimizes material strength and reliability, crucial for automotive and industrial applications. Advantages. The 12,500-ton press line delivers parts with exceptional dimensional accuracy and improved microstructure, reducing the need for subsequent machining. Its automated nature boosts production rates while ensuring safety and energy efficiency. This robust process, coupled with advanced automation, positions Balzers as a leader in forging technology, particularly for demanding applications like automotive axles. Forging a 9 inches 90-degree bend in a steel pipe to create a sharp angle. The process starts with selecting a steel pipe of the appropriate diameter and grade, typically made of carbon or alloy steel, depending on the application. To begin, the pipe is heated to a specific temperature, typically between 1,800 degrees Fahrenheit and 2,300 degrees Fahrenheit, depending on the material. This heating makes the steel more malleable and easier to shape. The heated pipe is then placed in a hydraulic forging press or specialized bending machine, where substantial force is applied to achieve the desired 90-degree bend. During the bending process, the pipe must be carefully controlled to avoid cracking, distortion, or weakening, especially when creating a sharp angle. In some cases, a mandrel may be used inside the pipe to provide internal support, preventing collapse or deformation as the bend is formed. The bending machine is precisely controlled to ensure the angle is sharp and accurate, while maintaining the strength and structural integrity of the pipe. After the bending is complete, the pipe is cooled gradually to prevent thermal shock and stress. Post-processing steps, such as heat treatment, may be applied to enhance the pipe's strength and durability, ensuring the final product meets the required specifications for its intended application.